that? Now, in general, what is the distance between that and that?
Time-like events.
So in this case, they are time-like events, indeed, because I did it.
Yeah.
It's a causality coming that what is successive. But then, right, so how would you measure this distance in terms of the geometric quantities that you have? Say you know the coordinates of both events, right? So you have, I can write it, right? You have clap 1. And clap 2. And I ask you what is the distance. So and you know this is x mu 1 and this is x mu 2. What is the distance between 1 and 2?
Well, if you have your coordinates and a siren.
Sorry?
Sorry, is your clap a standard siren?
So, let's say yes. In exactly the power of the clap.
Then maybe you could define a distance?
Then how?
Kind of how the energy dilutes, I guess.
Alright, so yeah, so this is a measurable notion of distance. So you think about something like luminosity distance. Right, so this is something, So this is one thing that we can, but you see, in this case you define it from, say, observable quantities, the power that I have emitted when I did the clap, and say the sound power that someone received with the ear. So you have two observable quantities, but I would like first to talk about something, how can I define it theoretically? Integrating the curves and things like this, can we actually have such a notion? You had an idea about it?
Yeah, if you already have the coordinates, you can just integrate in your coordinate frame.
But
right.
Along which which line?
That's
which
geodesic.
Which geodesic? Okay, so I have here two events that are separated by a time-like, say, a time-like separation. So, which kind of geodesic would you integrate them?
You need a metric, you need information about.
Yeah, so suppose you know the metric.
Proper length.
Proper length. So, right, so the notion of proper length would be something that, so maybe what you have in mind is something that, so suppose I have a curve, I don't define it so far, I have a curve on L, and you have in mind, I guess, something that's like the distance is the integral between, so over L, of something like maybe g mu nu, dx nu, square root of that. Right, something like this. So, why not? That's actually a very covariant way if we define properly what is this thing. It's actually a notion that makes sense geometrically. But there is an issue about that. For example, if I want, with this definition, to measure the distance between the event this light emitted a photon and second event I received the photon, I get that the distance is 0. And I don't want that, right? It doesn't make sense. The distance between this stuff here and me is not 0. We don't want a notion of distance that tells us that this is 0. So this is kind of okay, but it's not. It doesn't match. A notion of distance, intuitive notion of distance. You can think about now separated. So we need something more. Because so far, I think this is the only covariant way to define a notion of distance, right? We have just a metric, two events. The only thing that is sensible is to define something like that. But the bottom line is, when I said what is the distance between, when I said that if I consider two events like the emission and reception, it doesn't match the notion of distance that we have in mind. It's because actually what we have in mind is not the distance between two events. It's the distance between an event and a word line. Right? When I say, actually, so what's the distance between this event, emission of a photon, and me? But me, it's not an event. It's a full line of events. So the reason is what we have in mind defining distances is the distance between events and word lines. Or even distances between two word lines. So what is the distance between this light and I? So let's consider the first case. So in this case, I have something which is actually a bit clearer. I have a word line, and I have an event E. And now I wonder what is the distance between these events and this word line. Okay, so if the event is very close to the word line, there is actually no ambiguity. Because this is what we have done in the whole first two lectures when I was talking about proper distances on a screen, for example. I was just saying, well, I'm considering events that are all very close to each other. In particular, the distances, whatever this means, is very small compared to the curvature scale of space-time and compared to the accelerations that things can have. And I say I have a full velocity of an observer. This defines locally a hypersurface or a hyperplane that is orthogonal to the full velocity, that defines the simultaneity hypersurface. And then I just take the hypersurface that corresponds, that intersects with this event, and that tells me what the distance is. So if I have an event which is very close, so take U, I have here simultaneity hyperplane. I cannot really say hypersurface because actually I know that this is only valid when I'm very close. Right. Then I've got no problem to define this thing. If this is, say, 0 and this is delta x mu, then yeah, the distance between the event and the word line is just T mu nu delta x mu delta x mu square root of it. And I don't have the problem that I had previously because I know that by definition, in the way I defined this O on the word line, I prevent the separation between those two events here to be null separated. They are actually separated by a space-like separation, infinitesimal one. So this is if delta x mu is infinitesimal. Now what happens if it's not? Just to say that we have used this notion during the last two lectures. But yeah, now what happens with the separation is not infinitesimal. So if it gets on the order of the curvature radii of space-time, yeah. Now we get in trouble. We need prescriptions. So again, I have a word like an event. What can I do? Okay. Any idea? Yes.
Do you have to like choose a foliation and project your integral onto?
That's a possibility. One possibility is to define a foliation, indeed, that would typically, so for it to have a meaning, you would define a foliation that is everywhere orthogonal to the word like L, and then this will extend the notion of simultaneity hypersurface, and you find the one that matches E, and and then you have this distance. So that's, well, then you have another step, right? Because, okay, let me write that, because this is the first possibility.
But how is it that it can be orthogonal to this word line and it's everywhere?
Sorry?
Is it possible to have everywhere orthogonal hypersurfaces?
Oh yeah, well this is, you are free to do it, right? You can define a hypersurface, you know. You just start from it and you complement it as you want.
How do you extend to E?
Ah, okay. So suppose I have
Such a foliation.
just a foliation, do that, that.
So
Then you
there's-
find the one that touches
Okay, but the problem is that they intersect.
the intersect.
It's not clear, yes.
Might.
Ah, yes, okay. Well,
They might intersect.
they might intersect, but well, I'm just talking here about some possibilities that you have. You can always define a set of foliation that do not intersect. In which the hypersurface that you define do not intersect. You're always free to do that, right?
I think you're forgetting the fact that E is not an event static. It's also have a word line.
No. An event is static in the sense that it is a point in space-time.
It's not a source.
It's not a source, it's an event. Of course, if you have a second word line, then you need to define the notion of distance at a given time, things like this. But so far, this is just an event to make things easier.
Yeah, but maybe what he's saying is that to have an event, you have to have an observer at that event. So you have a word line.
Just think about no, just the abstract notion of event. You have a manifold and a point in this manifold, and this is an event.
Stuff is happening there. And you have an observer that doesn't know because it's not observing that.
Well, that's okay. So then you go to the next problem, which is even if we manage to define a notion like this, in general, it's not observable. So, but this is the next step, right? First, you do theory, and then you realize that it was useless. But so, okay. But just to finish on that, yeah. So Amadeus says, define foliation. So it's the first possibility. Foliation. So you have a foliation of space-time, orthogonal, say, to the line, to the word line. So a set of sigma of tau hypersurfaces. Find tau such that E belongs to sigma of tau. And then, once you have done that, well, you get a three-dimensional hypersurface that has its own metric, the induced metric. And then, for example, you can define the unique, well, we suppose that it is unique, space-like geodesic between E and the intersection between the hypersurface and the world line, and then you get a notion of distance. So this is what I would call the the foliation spatial geodesic distance. Right. Then draw geodesic on sigma. So it wouldn't be in general a geodesic for the full metric, it would be a geodesic of the induced metric on sigma, which is a bit different. With respect to, for example, I would call H nu, the induced metric on sigma. And integrate. And that gives you a notion of distance. Okay. But you see already the weakness of this definition is that it is foliation dependent. Right? So I can draw something like that, but I could also draw something like that. And they do not belong to the same hypersurface, and therefore the notion of distance dependent is completely different. Or just to mention something important about this notion of
foliation by orthogonal geodesics.
But it's the same, right? Because you would have, if you start from a given, if you start from a given family of geodesics that are completely
No, the orthogonal to the world line. You define geodesics orthogonal to the world line, that will give you a unique foliation.
Oh, no, it's not. No, because, for example, it could be, okay, let me draw it again. See, if I have a thing like this, I can start being orthogonal here, but doing something which goes like this, or like this.
Yeah, but you propagate geodesic.
Ah, okay. So you say you okay, right? Now this goes to the second notion, which is very interesting. Good. Yeah. So you say I've got a tangent, an orthogonal vector here, and I parallelly propagate it, transport it. Here I get something, and I construct by parallel propagation. Yes. So this would be a very special. Okay. So I thought you were talking about time-like geodesy, but you were talking about space-like geodesy. Good. Okay. So that would be a specific notion of foliation, which would be foliated by space-like geodesics.
Yeah, the Gaussian coordinates.
By Gaussian coordinates, exactly. That's so. Charles says. I foliate with Gauss, actually Fermi normal coordinates.
Yeah.
Yeah, so this is a notion which is foliation independent, indeed. And so they would correspond, so the first way to see it is to say, I'm starting from here and I parallelly propagate some vectors everywhere and I construct a foliation. I do that everywhere and I find the right form, the right hypersurface that touches my E. Another way to see it, which is completely equivalent, is to say I find the only space-like geodesic that connects the E and the world line in an orthogonal way. So that would be, therefore, the spatial geodesic distance, equivalently.
If your curve is arbitrary, it's not guaranteed there's only one orthogonal.
Oh yeah, so let's suppose that they are not too far away and that the metric is not completely crazy. That's, that's the idea. Yeah, well, of course, If we want to do it mathematically, fully mathematically, it's really a big problem. Here we try to accommodate with the mathematical difficulties and try to keep them reasonable.
Stationary geodesic? Stationary geodesic from the point of the curve?
Stationary geodesic.
Stationary length.
Oh,
Minimum, maximum, whatever.
yes. Right.
No, I know what you're leading up to anyway. So.
Okay. I can find unique, so space like geodesic connecting E and L orthogonally. Right, so that's another way. Yes, and by the way, this is also what externalizes, what stationarizes the distance between the event and the world line. We can give at least two others. There is the radar distance. So in this case, I consider not space-like geodesics, but null geodesics. So in this case, I have an event. I consider the light rays that are connecting the event on the past, the future null cone, the past null cone of this world line. I say this is proper time tau 1, proper time tau 2. And this I would define D, so this would be D radar as tau 2 minus tau 1 divided by 2. That's another way. Another one. I can use the affine parameter. Right, so I could say, for example, I get so here lambda 0, lambda 1, lambda 2, and I can define the D affine as being, for example, lambda 1 minus lambda 2, or why not? There are a few definitions possible. Lambda 2.
What is the affine parameter that is not tau? Affine parameter along what?
Oh, sorry.
Are we talking space-like, time-like paths?
No. Yeah. So this would be the null distance.
All right.
So I have lambda. Okay, we take lambda 2 minus lambda 0 divided by 2. Any combination of that. But the important thing is that in all those notions, in general, they're all different. They all give you different numbers. So this was just to mention the difficulty that you have in general to define the notion of distance in GR when you're looking at objects that are separated by distances which are, well, considerable, not infinitesimal. As soon as you can work as if you were in spatial relativity, so locally, using local flatness, then things work quite well. But in general, the notion of distance is ambiguous. So, and as you said, Renato, in general, they're also non-measurable, right? Because you cannot go to the event that was considered and do your measurements. Except this one. This one is the only one that is actually measurable in all those notions that we have discussed so far. So, problem. Not measurable, except the radar.
And radar only if you're old enough.
If you're old, yeah, if you're close enough, and then you go to the problem of what is the interest of that if I'm trying to measure distances to objects that are at a distance comparable with the curvature of space-time like this. This is, but in practice it's hard.
Even, I would say that even with knowledge it's not possible to use this radar. I don't know, yeah. Because I think what E the event is like light being emitted by a star. So I cannot send a light ray to a star and ask the star to send a light ray.
Yeah, agreed, that's the problem. So, and that's why we use that only in the solar system. So we do that daily with the lunar laser ranging experiments, so to measure the distance to the moon, so the distance that we use. So okay, let's go to the measurable distances. Yeah. And indeed we can start with discussing this one. So there is the radar. Oh yeah. So we use it for the moon. In the solar system, it was used also to measure the distance to this probe. Which one? Well, I think it was used for the distance to Saturn as well.
Yeah, you can use it for relatively, I don't know about Saturn.
Okay, let me check.
Hard surface planets.
Yeah, but it was used, I think, to measure the distance to Saturn using a probe, using I think it's that. But yeah, moon, solar system, in general. Oh, by the way, it's also the notion of distance that you use when you're doing gravitational wave experiments. Right? The way we measure gravitational waves, when we say that when we have a gravitational wave that goes in an interferometer, it increases the length of the interferometer, it reduces then so you have this thing happening. Then the notion of distance, when you say distance is increasing or reducing, the way you measure it is through this notion of timing, right? Because the interferences are due to the timing of going back and forth with light rays. So I could say also in interferometers. But as you said, as soon as you go outside from the solar system, it's a bit of a problem. So then, how do we measure distances to stars? So we go a bit further and say, what about our galaxy? In the Milky Way. Right, so this you all know is the parallax. Parallax distance. And I'd like to spend 10 minutes talking about the parallax distance from a space-time perspective. And how we can relate this to what we have discussed in the previous lecture. So the way we can see the parallax is the following. So you have a source from which we are going to consider light to emerge, in this case. And we have the sun and the earth. We'll do a 3D diagram like this. And consider now a light beam that is emitting continuously by this source. Something like this. That it matches the orbit of the Earth around the Sun. And I didn't do straight lines. Right? This is intended. So, and also I specified a bit the thing so that the source appears to be really on an axis orthogonal to the ecliptic plane, so that it's a bit easier. All right. So you know the principle, right? So if you are on the Earth, you're looking at this source of this star. So you can even do star. And you look at the change of position, apparent position of this source on your sky. So if you look at apparent motion, it gives you something like that. Something like this. It's the same. Yeah. We can measure, so this will draw a curve, a closed curve in our sky. We can measure the size of this curve, omega observed. And the way we infer the distance is by taking the ratio between the area of our orbit with this angular aperture, so the angular size of the apparent motion. It's quite easy to see that in flat space-time it gives you the notion of distance that we want to get. So parallax distance will be the area of the orbit divided by the apparent motion.
You need a tilt angle in there. You need a tilt angle.
Yeah, I forgot the tilt angle. Yeah, just this is why I said I take something which is orthogonal, just to make things simpler. It's also because it's easier to relate to what we had discussed previously. So now the thing is to relate this to what we had discussed before. Right, so connection with lecture 2. Yeah, so this thing is the area of the beam at the observer. The area of the beam at the observer, if I consider an infinitesimal beam, I can write it, you remember, like this. So this d2 psi at the observer. And this, well, it is the angular aperture of the beam, but actually seen in a different way. It's not the angular aperture here when it converges. It corresponds to the derivative with respect to the affine parameter of the beam, so the angle of the beam, but at the observer when it has a non-zero size. So this is actually d2 psi dot at the observer with the fractional change. The frequency factor that translates, remember angles into derivatives with respect to the affine parameter, and yes, which goes here. And if you remember the definition of the deformation rate matrix, SAB, which I wrote, it's like this. Well, you recognize here the determinant of it. So when you have gravitational lensing, or curved space-time in general, the parallax distance is related to this deformation, to the determinant of this deformation rate matrix. So this tells you you can show that these determinants actually it tells you something interesting. Is that the parallax distance satisfies a kind of defocusing theorem. Whenever you have gravitational lensing, it decreases theta, increases sigma. So this thing is always bigger in, it's always smaller in curved space-time than in flat space-time. So the parallax distance is always bigger in curved space-time than in flat space-time. This is any gravitational lensing phenomenon. Right, so this was about the parallax.
Is this like ever taken into account when people measure parallaxes?
No. Of course, because in our, well, gravitational lensing events in our galaxy, well, you have micro lensing events, and they are actually in this case it would be non-negligible, this thing, but it's never taken into account. And by the way, I think this does not exist in the literature. I've seen two references in which people were interested about the parallax in curved space-time, but they didn't have the sigma term. So there was a paper by Sachs, Ehlers, and things maybe in the 60s, and no, not in the 60s. Actually, maybe, but it's a very long time ago. And they showed that they had the theta, but they forgot about the sigma. Well, which is always smaller anyway. Oh, note by the way that this theta and sigma are not exactly the same as the one that we mentioned previously, because previously we had the picture in which the beam is converging to the observer. Here it's converging from the source, so it corresponds to the different picture. And the way the Ethereum reciprocity relation applies in this case is not very easy, because we are talking about not about D but about S. So there's a bit of work to do here.
Parallax doesn't get beyond the nebula.
Well, that's the thing, yeah. Anyway, the cosmological things would not be affected by that. So that's also why it's not very relevant. It's just for the beauty of it. Okay. Okay, let's talk now about another notion of distance. The one that you mentioned, Tony, is actually the last one I wanted to talk about. The luminosity distance one. But yeah, so angular diameter distance, of course. So the one that we're using in laser distance, we are using that for the CMB. We're using that for bioacoustic oscillations, for the fraction of gas in clusters. It's actually a notion of distance that is very used a lot in astronomy and cosmology. So yeah. So here it's the most natural notion of distance that emerges from the whole formalism that we had developed in the previous lecture. So it's just that when you are observing a given source, this source has a given area, you observe it under a given solid angle, and you just divide the area of the source divided by its apparent size. So you all know that very well. And given what we have done before, you know that this is omega 0 determinant t squared. And also given the focusing theorem, you know that's the angular, so because it's related to the area of the source, the area of the beam, it is always, so the area is always decreased So the distance is always decreased by gravitational lensing phenomena. It's the contrary of the parallax distance. But besides that, what I wanted to mention is the effect of geometrical aberrations. It's one of the reasons why I kept this omega 0 all the time. So consider two observers that are observing the same thing, same galaxy, say. But one is static, but the other one is moving with the velocity v, say, with respect to the first observer. Suppose that they are making a measurement of the apparent size of the galaxy at the same time when they coincide spatially, and they compare what they are seeing. The result is given for free, because you have dA from the observer 1, which is given by the frequency measured by observer 1, determinant of d square root. But this thing is a purely geometrical quantity. Right? It doesn't depend on the observer that measures it. While this does. So dA of O1, dA of O2 is omega 1 of omega 2. That's why the effect of aberrations that we study when we are doing special relativity goes exactly like the redshift. It's because actually the information about the full velocity of the observer is contained in the frequency that multiplies this geometrical object. But an important thing to realize here. So yeah, just to say, so if I'm moving towards the object, the frequency increases. The frequency decreases. Right? I'm blue shifted. Sorry. Yeah. Going to do that correctly. So blue shifted. So I see the thing smaller. So I'm moving towards the object. It appears smaller. When I'm moving backwards, it appears bigger. It is the effect of aberrations. And yeah, this situation, and I want really to insist on that, breaks the degeneracy between the velocity of the observer and the velocity of the source. Those two things are not equivalent with respect to this measurement. Because here you see, it depends on the velocity of the observer, but it doesn't depend on the velocity of the source. If the source has any motion, it doesn't change at all the measurement of its angular distance. And it's something that could seem weird, because you say, well, but if I'm, for example, working in special relativity, I cannot distinguish between the velocity of the observer and the velocity of the source. But the fact that you are measuring something like this with a beam that converges to the observer and that is finite at the source breaks the symmetry between those two velocities. So the full velocity of the source and the full velocity of the observer do not have the same status in this measurement because of this picture. Right. So that was about aberrations. And now let's go to the last, but not least, the luminosity distance. So in this case, it's the opposite picture. You have an observer with a telescope. You have a source will make a big telescope. And you have a source that emits light, and we consider a light beam that is converging, or that is emerging, sorry, from the source. We remember the luminosity distance, you define it as the ratio between the luminosity of the source divided by 4 times the intensity that you observe, luminous intensity, so power per unit area. This is really based on the Minkowski idea that when you have when a source emits a spherical wave, the power is homogeneous. If the source is isotropic, that the power is spread on a sphere that is bigger and bigger, and so the power goes like the inverse of the radius squared. To get the radius, then you can measure, compare the power emitted with the intensity that you observe. So that's just based on this idea. Anyway, all those things, all those definitions, they are based on ideas that were developed in flat space-time, right? They are inspired from that. It's just that we realize that we can still define distances like this, just that they differ at the end when you are in curved space-time. All right, so we can rewrite a bit this thing. In particular, we would like to connect it to the Jacobi matrix and all the formulas that we have developed so far. So let's do that. Okay, so for that purpose, I am going to make a further assumption. I will assume that the universe is transparent and does not absorb or emit photons. So the photons that are emitted within this cone, angular cone, by the source are all received at the end by the observer. No more, no less. So if we consider during an interval of proper time in the source frame, the number of photons emitted in the cone omega s. So this thing is, by definition, well, so that's even detail. So this will be dn equal. So first, total number of photons that are emitted during this period is just the luminosity time d tau s. So this is the energy emitted. I divide it by the energy of the photons to get a number of photons. And I multiply it by a correction which corresponds to just the portion of the photons that are emitted in this cone. I suppose that the source is emitting isotropically, so that the fraction of photons that are actually emitted in this cone are just omega s equal to v by 400. So far so good. So now I keep this number of photons, and I know that during this period, so this fraction of photons, they propagate without being absorbed or anything, and they are observed by the observer during a period of time that corresponds to the period of time emitted, but in another frame. So during d tau 0 corresponding d tau O corresponding to d tau S, the observer receives the same amount of photons. But which is also equal to if now I use the quantities, the observables that are evaluated at the observer, well, the fraction of energy that is received is the intensity that is observed multiplied by the amount of time. So this is an energy per unit area. So I multiply by the area of the telescope. That tells me what is the amount of energy that is actually collected. And I divide again by the frequency, but now which is the observed frequency. I equate those two things. I will isolate on the left-hand side what will correspond to the luminosity distance at the end. So I have this L star that will be divided by 4 pi here, and I0 that I divide by this. And what's remaining is, on the right-hand side, A0 divided by omega s. I have also d tau 0 divided by d tau s, and omega 0 divided by omega s. Alright? This is luminosity distance squared. This, by definition, is what we call the redshift. I mean, 1 plus the redshift. If you think about the redshift not as a shift of frequencies, but about the shift of time between the emission of two photons, or the time between the two maxima of a wave, you realize that this thing is actually equal to that. Right? So the time between the emission of two successive events at the source and the corresponding time at the observer is also 1 plus e. So in the end, we have TL, which is 1 plus z squared, the square root, so just 1, A0 over omega s. Almost there. We almost have the angular distance. Right? Small difference. It's A0 over omega s and not AS over omega 0. And now Etherington reciprocity relation comes to help us. We write that so A naught over omega s. So this thing is omega source, determinant of t evaluated from the source to the observer, while, if you remember, we had a source over omega naught equal omega 0, determinant of t starting from the observer. What happened?
An event?
That's okay. But we Etherington says that the determinant of t is always equal to the determinant of t OS. So square root of A over omega s is equal to omega s omega O, sorry, squared, yeah. And therefore, so which is 1 plus z dA. So we have this which is 1 plus z dA, so we get dl equal 1 plus z squared dA, the famous distance duality relation. Okay, so what I would like to emphasize here is the nature of the two here. So I have heard multiple times people who presented this relation saying that in this square they have one factor 1 plus z that comes from the fact that the photons are redshifted, so the energy that comes in the definition of the luminosity distance RF, well, you have this energy 1 plus z for the redshifting of photons, and another 1 plus z which comes from the time delay, so the fact that you emit more photons in one frame than you receive in another. So this is wrong.
Yeah. Second.
Just one second. So this is actually wrong, because as you see here, those two effects, redshifting of photons and time delays, they are actually coming as a square, but then you take their square root in the definition of the luminosity distance. So 2 here is 1/2 plus 1/2 plus 1. This is redshift. This is time delay. And this is Etherington. Or if you want, it's aberration. It comes from this change of point of view between converging and the observer or emerging from the source, in which the 4 velocities of source or observer